Good evening. Tonight we welcome our speaker, Dr. Adam McMaster, an astronomer and postdoctoral researcher at the University of Southampton. His work specialises in the use of citizen science to find rare and interesting things in large astronomical surveys, especially black holes, with the website @BlackHoleHunters. Currently, he is searching for the gravitational micro-lensing signatures of black holes in data from the TESS satellite. Adam is also the editor of an online astronomy newsletter called 3 Alpha. So let's give Adam a big Mexican and Swinton welcome.
Good evening. Thank you for having me. Let me just share my screen. Right, hopefully you can all see that. Yeah, so what I want to talk to you about tonight actually has nothing to do with any of the research topics that you just heard about. This is actually something I studied as a small part of my PhD thesis, which I finished last year at the Open University. So I want to tell you about a star which behaved very strangely in the mid 19th century, and ever since then has behaved more or less normally. So it's all a bit of a mystery exactly what happened back then in the mid 1800s. So the star, as you probably guessed from the title, is called HD 38451. This image here that you can see is an image from the Digital Sky Survey. HD 38451 is this bright star. Hopefully you can see my mouse pointer. This bright star here in the center. So if you look at that star today, it looks more or less unremarkable. It's not currently doing anything terribly out of the ordinary. But if you did want to find it, it's roughly here in the night sky. I should say this is a bit of an old screenshot from Stellarium, so Jupiter is almost certainly not in the place that it is in this diagram. But if you're interested in finding HD 38451, it's just there between sort of Taurus and Orion. It has a visual magnitude of about 8.9, so you won't see it with the naked eye, but you may be able to find it with a telescope. So the story of HD 38451 starts with a man called John Russell Hind, who was an English astronomer. He was born in Nottingham, and after school he worked at the Royal Observatory Greenwich for a few years in the early 1840s, and he left Greenwich to become the director of a private observatory called the George Bishop's Observatory, which was presumably owned by some rich guy called George Bishop. While he was there, he observed HD 38451 while he was looking for variable stars. He was carrying out an observing campaign looking for new variable stars. Those are stars which change in brightness for various reasons, and we'll hear more about that in a moment. After his time at the George Bishop's Observatory, he later became superintendent of the Nautical Almanac, and he did a lot of early work on asteroids and did eventually end up discovering several new variable stars. So about HD 38451, this is what he wrote about what he discovered in a letter to the monthly notices of the Royal Astronomical Society. He wrote, "On September 3rd, 1848, a star of a very red colour was entered on a chart. As I have repeatedly met with reddish variable stars, this object has been closely watched since the above date, but no alteration was perceived until the evening of November 14th, 1850, the year he was writing this, when I found the star decidedly bluish, the red tinge having vanished entirely. Perhaps it would be most accurately described as bluish white." So that is actually, I've cut out a small bit from the middle there, but that's almost the entirety of his write-up in the monthly notices. There are no hard data. There's no objective measurements. It's just his subjective description of what he saw, and that's typical for astronomical research of the time. But he was an experienced observer, so even though we don't have any numbers to work with here, we can more or less trust his assessment of what he saw. So he saw the star. The first time he observed it, it was very red, and then just a couple of short years later, it had gone, all the red color had vanished entirely, and it was bluish white. Um, so these days we would put numbers on that, and we would measure the color. We have ways of objectively measuring how red or how blue a star is. But we can trust his assessment. He would certainly have been able to tell the difference between a red star and the blue star. Now, what's interesting here as well is that he says he was watching it closely since he first observed it. Excuse me. And saw no change at all until November 1850. So that sounds like he was repeatedly observing it during those 2 and a bit years. We don't know exactly how many times he observed it on what dates, but it sounds like this change in color happened very suddenly from one observation to the next. It didn't happen gradually over the course of the 2 years. And even if it had happened over the course of the 2 years, that would still be a very rapid change in color. So something very unusual appears to have happened here. The other notable thing is that he didn't mention any change in the magnitude of the star, in how bright the star appeared, which is unusual as well. Most of the phenomena we know about that cause stars to vary would also change the magnitude, and that doesn't appear to be the case here. So let's talk a bit more about the colors of stars. Here's that image again from the Digital Sky Survey. And you can see here, I'm sure all of you are familiar with the fact that different stars are different colors. HT 38451 and a few of the other bright ones here are more or less white. There are many red stars here, some bluer stars. So it's not unusual for stars to come in a range of different colors. And that has to do with their what type of star they are, how big they are, what stage in their lives they are at. It's also not that unusual for a star to change color per se. Stars do change color over the course of their lifetimes, but it tends to take a very long time. Perhaps millions or billions of years, or at least thousands of years. Certainly not 2 years, and certainly not a matter of weeks or months, however long the period of time was between his two observations. In particular, when we talk about red stars, it's important to remember that red stars tend to be the older stars. So young stars tend to be bluer, and red stars tend to be older. So when we talk about a change in color, it's usually the other way around, from blue to red. So the most famous red giant in the sky, Betelgeuse, for example, used to be confused with Saturn in ancient times. There are actually written accounts from, I think, ancient Greece, where observers would confuse the two. That's how much the color of Betelgeuse has changed in just a few thousand years. Saturn, of course, is the same color it's always been. Betelgeuse used to be a very distinctive yellow-white color and has now started to reach the end of its lifetime and has turned a very distinctive red color. But is there a way that stars can get bluer? Well, let's go and look at where the color of stars comes from and how that changes throughout their lifetime. This is a diagram called the Hertzsprung-Russell diagram. It's probably the most important diagram in astrophysics. This is what you get when you plot a graph of the temperature or the color of stars on the horizontal axis against how bright the stars are on the vertical axis. So here the temperature is measured in degrees. You can also do various measures of color as well when you end up with more or less the same diagram. And on the vertical axis is luminosity. It's worth remembering that's how bright the star actually is rather than how bright it appears to us. So you have to take the distance to the star into account. Further away stars will of course appear to be less bright than closer ones. So taking the distance into account and coming up with a measure of how bright the star actually is, you get a diagram like this. And what you find is if you take all the stars in the sky and you plot them on the HR diagram, they mostly sit in a few key areas on this diagram. The vast majority will be in this this diagonal band across the middle. which is named the main sequence. That's where stars spend most of their lives. Now, the fact that I've said that they spend most of their lives there tells you that they don't spend the whole of their lives there. They tend to, when stars first form, so stars form out of collapsing clouds of gas, collapse under their own gravity, and eventually the density of the star gets to the point that nuclear fusion can start. That the star will tend to be around here, just under the sort of between the main sequence and the giants, at that point. At the point that nuclear fusion starts, the star will then move on to the main sequence, and it will stay there for the majority of its life. So for the sun, that's that's going to be the best part of 8 billion years. For the larger stars, which are at the bluer end, that will be much less time. And for the smaller time, for the smaller stars, it could be even longer. And what you tend to find is the various spectral classifications match the position on the main sequence here. So the largest O-type stars are up at the top end here. They're the bluest stars, and then the M dwarfs are down at the bottom. They're the reddest ones. Once stars start to run out of fuel and get to the end of their lives, they tend to expand and they tend to get redder, and then they move from the main sequence up into the giants and supergiants areas, depending on where they start. So the bigger stars become supergiants. The stars like the sun will become giants. Eventually, depending on how large the star is, the larger ones will explode in supernovae and create black holes. The smaller ones, like the sun, will simply shed their outer layers. Their core will collapse a bit and get a bit denser, and then you're left with what's called a white dwarf. A white dwarf is basically the exposed core of a star. And the white dwarfs tend to be hotter, but also less bright. So they tend to be, they're down here on the bottom left. Now, where is HT38451 on this diagram then? Oops, yeah, there it is. HT38451 sits just about here, so it's bit bigger than the sun. It is on the main sequence, but it's sort of at the upper edge of it. And that's interesting because that potentially means that it's quite close to an area of the diagram where a lot of variable stars tend to be. Hind wrote that he was interested in red stars in particular because they tend to be variable. And the reason for that, if I switch to this version of the HR diagram, this shows various kinds of variable stars. Don't worry about what all the different kinds are. What we're really looking at here is it's where the stars, the variable stars are. So what we're seeing on this is in particular, pulsating variable stars. Those are stars that are thermally unstable. And so they tend to heat up, they expand, they physically get larger. When they get larger, they also get brighter and they also get redder. And then because they're brighter, they're radiating more heat, they cool back down, they shrink, and then they tend to get less bright again. The majority of those stars are here in this band here, between the main sequence and the giants. And that's an area called the instability strip, where stars tend to transition through that area to become giants once they start to run out of fuel. So HG38451 is right at the bottom of the instability strip. So that kind of makes sense that if you were interested in variable stars, this is a star that you might keep an eye on. And that maybe could be a hint that maybe there's some chance that it is a variable star, and that maybe that might have something to do with this strange change in color. So are there any variable stars that change color? Well, as I've just said, the pulsating stars tend to get redder during pulsations, and then they get a bit bluer again once the pulsation ends. So perhaps what Hind saw was some sort of large pulsation. Well, the problem with that idea is that the red color lasted for at least almost 2 years. It might have been, who knows how long it was red before Hind first observed it. And that would be a very long time for a stellar pulsation. Most of the pulsating stars you see on here, each pulsation will last a matter of hours or days or weeks. The long period variables, that's these ones over here, the LPVs, their pulsations tend to last a few months. A pulsation that lasts years would be very unusual. And also, most of these pulsating variables are what are called periodic variables. Their variations, their pulsations repeat on quite predictable timescales. And as I mentioned at the start, HT38451's change in color hasn't repeated, it just happened the once. So the idea that this could be some sort of stellar pulsation doesn't seem to hold up. But having said that, if you look in the scientific literature, there are a few mentions of HT38451 being a variable star. An astronomer called Hans Ulrich Sandig in 1950, in a paper where he's simply describing a variety of variable stars that he's worked on, describes HT38451 as weakly, irregularly, and slowly variable, but he also doesn't provide any data to back that up. The Simbad website, which, if you're not familiar with it, is a very useful tool which gathers data for a wide variety of stars. Most of the stars that you can see by the naked eye, or any star that has a name, will certainly be on there. It collates all the sort of all the different observations that people have made and gives you a listing of the recent scientific papers for each star. The Simbad page for HT38451 lists it as a pulsating variable. Again, none of the scientific papers seem to provide anything to back up the assertion that it's a pulsating variable. So I don't think it is, and as we'll see in a little while, I've done some of my own work on the data for this star, and I don't see any evidence of pulsations either. So far, I've described a lot of vague observations that people have made and very little hard data that anyone's produced. Luckily, there is some hard data out there, thanks to two astronomers called Warner and Snedden, who in the late 80s, also in the monthly notices of the Royal Astronomical Society, they published a very good write-up of HT38451 with some very good spectroscopic observations. So they carried out a load of spectroscopy and they learned a lot about the star. Before I get into what they learned, let's take a moment to talk about spectroscopy, because spectroscopy is one of the most useful tools that we have in astronomy. It's actually, honestly, a little bit silly how much we can learn from this one technique. So spectroscopy is basically where you put a prism in front of the light from a star and you look at how bright it is across different wavelengths. When you do that for different types of star, you see spectra that look very much like the examples on here, where different types of star will be brightest at different parts of the spectrum, and also you tend to see these dark lines in the spectrum, and those are called absorption lines, and those come from the different chemical elements and molecules that make up the gases that are in the star. And very luckily for us, each different element and substance absorbs a unique set of very narrow wavelengths when light passes through it. So what that means is when you have a spectrum of a star like this, it acts as kind of like a barcode. You can look at these lines and you can figure out exactly what the gas is made of. So this works for figuring out the chemical composition of stars. It works for looking at the atmospheres of exoplanets or nebulae. If you read a headline where they found such and such a planet and it might have oxygen in its atmosphere or whatever, it's this kind of spectroscopic data is how astronomers figure that out. And this is actually how the element helium was first discovered. Nice bit of trivia. Helium is actually named after the sun because it was first discovered in the spectrum of the sun when spectroscopy was first invented. So that tells us about chemical composition, but there's also a lot of a lot of other things we can learn due to the sort of effects of the Doppler effect as molecules are moving around. So you're probably already familiar with the Doppler effect. That's where if an object is moving towards you and emitting some sort of wave, light or sound, that wave is sort of compressed and moved to higher frequencies, higher pitch if the object is moving towards you, or lower frequencies when the object is moving away from you. So what that means is if we look at the spectrum of a star and we know what spectral lines it should have, because they're all more or less the same. There's some variations, but there's certain spectral lines that you'll see in every star. Then you can look at what wavelength you observe that spectral line at, compare that to what wavelength you know that line should appear at, and then you can figure out how much the light has been Doppler shifted, either blue shifted or red shifted, before it got to you. So then you can figure out how quickly the star is moving away or towards you. Now that also can let you work out how hot a star is and how quickly it's rotating. Because if you imagine a cloud of gas which is hot and all the molecules, because it's hot, all the molecules in that gas are moving around at random. That means some of them will be red shifted because they happen to be moving away. Some of them will be blue shifted because they happen to be moving towards you. And what that does is it has the effect of broadening out the lines in the spectrum. So what I've shown here is actually an emission line. So as well as absorption, molecules can emit light at specific frequencies as well. And it's very much the same sort of effect in the spectrum that you can see that the line being either red shifted or blue shifted. So if you're seeing the collective effect of how all of the molecules in the gas are moving, then that broadens the line out if the molecule's hot. It also broadens the line out if the object is rotating. So if you imagine a star that's rotating, half of it will be rotating towards you, and half of it will be rotating away from you. So you see the same sort of broadening effect. So that's what Warner and Snedden were looking at when they studied HT 38451. And what they found was that the star is rotating up to a maximum speed of 200 kilometers a second. Now, I say a maximum speed because what they don't know is what angle the star is at. So if you imagine if it's face on, they'll see a much larger Doppler shift than if the star's at sort of a funny angle. But they can put an upper limit on the speed of 200 kilometers a second. And that is really fast. I know in astronomy it's quite hard to tell sometimes. We rattle off a lot of large numbers, so it's hard to tell which ones are unusually large and which ones are just normal. But 200 kilometers a second is extremely fast for a stellar rotation. That's actually almost fast enough for the star to just tear itself apart from the centrifugal forces. So that's quite a remarkable measurement. They also found evidence of circumstellar material, so material orbiting around the star. So they see two rotation speeds in there. They see the 200 kilometer a second rotation of the star, and then they see a slower rotation from the material that's orbiting around the star. Now, if you put those two things together, you realize that that means HT 38451 is a type of star called a shell star. And that's a star that is rotating so quickly and getting towards the end of its life where any kind of slight instability, it's not quite pulsating, but any kind of slight instability is enough to just push material off of the surface of the star. Because it's so close to pulling itself apart anyway, it doesn't take much extra force to just expel material into space. And that's called a mass loss event. And that potentially explains at least some of what Hind observed in the 19th century. So shell stars you may not have heard of. I hadn't heard of them until I started studying this star, but there are some that you'll certainly be familiar with. So on the left there is the Pleiades, obviously. One of the stars there is Pleione, which is a shell star. On the right is Gamma Cass. That's the center of the peak, the central peak of the W of Cassiopeia. These are two shell stars in the night sky that I'm certain everyone in the room has probably looked at before. So shell stars are characterized by three things: very fast rotation. They're at a later evolutionary stage, meaning they're at the later stages of their life, and they undergo mass loss events. So those three things potentially explain the change in color. And the reason for that is what effect that expelled material, that mass that has been lost, has on the light that passes through it. This obviously is a photo of a sunset. Um, and the effects you see in a sunset are more or less the same effects that are potentially at play in these observations of this star. So there are two things that happen when a star expels material. The gas and dust in that material can cause an effect called extinction. That's absorbing some of the light that's passing through them, decreasing the magnitude of the star and making it appear dimmer. It can also cause an effect called reddening, which is exactly what you see here in the sunset as the sun reaches the horizon. More of the sunlight is passing through more of the atmosphere. You see more reddening. So reddening is basically the scattering of blue light, which makes the source appear redder. That's similar to what's called Rayleigh scattering, which is both what makes sunsets red and is what makes the sky blue. So if you're looking at a sunset, or even if you're just looking at the sun is a white star, but it appears yellowish to us through the atmosphere because when you're looking at the star, some of the blue light has been scattered away, so you're seeing redder light than the sun's actually emitting. That's also why the sky is blue. So if you imagine the sun is over there and you're looking off in the opposite direction at the blue sky, the blue light you're seeing is sunlight, obviously, but it's sunlight that's gone all the way past you, been scattered off something in the atmosphere, and been reflected back to you. And blue light is scattered much more easily than red light. Now, in astronomy, this effect is really important because there's a lot of space isn't really empty. There's a lot of material between the stars within the galaxy. So the interstellar medium contains gas and dust, which can cause reddening and extinction on the scale of the galaxy. So if you're studying stars on the other side of the galaxy, you need to know exactly how much reddening and extinction that light has undergone so that you can actually study the star rather than the effect of all the dust and gas between you and the star. So as I said, mass loss events can cause these effects. Probably the most famous mass loss event, again, takes us back to Betelgeuse, the so-called Great Dimming of Betelgeuse in early 2020, late 2019, I think it was. That was caused, we now understand, by a mass loss event, by material being expelled from the star and orbiting into our line of sight and blocking some of the light from Betelgeuse. It made Betelgeuse a lot less bright, but also would have made it a bit redder. Hard to tell on a star that's already so red, but there you go. So the likely scenario is that sometime before Hind's first observation in 1848, HT 38451 probably underwent some sort of mass loss event. Some large amount of material was expelled, and when Hind observed it for the first time, that material was in his line of sight, causing reddening of the star. And then, by the time of his observation in 1850, that material had either dissipated or orbited out of the way. But there are still some problems with that. As I said, he didn't mention the star's magnitude changing, and any material from a mass loss event that could have caused reddening should also have caused a change in magnitude. It should have made the star less bright. Hind didn't mention that, and he was an experienced observer. We can't say for sure. Maybe he was just having an off day. But if the star had changed in brightness by a couple of orders of magnitude, he almost certainly would have written that down. There's also the question of why would the shell material dissipate so suddenly? Hind said he'd been keeping a close eye on it, and he saw no change at all for over 2 years, and then suddenly it changed dramatically. So maybe we can put all this down to the imprecise nature of the observations. Maybe he just was in a hurry or having an off day and didn't write down all of the detail, but we can't really be sure. And what about those reports of variability that I mentioned? A few people have observed this before, and they say it was variable. It doesn't appear to be variable now. So what's going on there? And that brings us to my own research, so the work that I did during my PhD. So my PhD was all, and the work I do now, in fact, is almost all involving a technique called photometry. That's basically measuring how bright stars are over time. So this here is an example of the measurements of a pulsating star. And you see these distinctive sawtooth patterns are what you see in the brightness of a pulsating star. And different types of variable star have very distinctive patterns. You can tell what type of star you're looking at just by taking these brightness measurements over time. So for HD38451, I started with observations from this space-based observatory called the International Gamma Ray Astrophysics Lab, or Integral. Now, I didn't use any gamma ray observations in my work, but all of these space telescopes have sort of wide field cameras on board to help them track the stars and make sure they're pointing at the things that they're intending to point at. That data is also useful for photometry. Any kind of regular photographs of the sky can be used to produce photometric measurements. I should also say this type of graph is called a light curve. So when you plot the brightness of a star over time, that's called a light curve. So the team behind Integral have published light curves of all of the stars that happen to be in their sort of pointing observations. And it was actually, I should say, it wasn't me that started this bit. A colleague of my supervisor was the first one to sort of flag this, but he looked at the light curve of HD38451 from Integral. It looks like this, and he found he did some analysis of whether or not there could be periodic variations in this light curve, and found evidence that there could be. So first thing to realize with this light curve is that it does look quite different from the example I showed you a moment ago. So this example has lots and lots of measurements, lots and lots of observations, and shows a very nice smooth curve. This is much more sporadic. Remember that these observations don't come from deliberate observations of this star. You get data from Integral whenever it happens to be pointing in the right direction for the star you're interested in. In this case, it happened to observe HD38451 every few days. It would take a bunch of measurements and then not see it again for several days. But still, there are techniques you can use to analyze this sort of data and look for periodic variability. And to do that, you plot this sort of graph. This is called a periodogram. Basically, this shows different frequencies along the horizontal axis. So, for example, a 50 on here means that there's something changing 50 times per day, and then on the vertical is just a measure of power, so how strong that change tends to be. So what you're looking for is, say it was a pulsating star that pulsated once a day, you would see a large peak around about 1 on this graph. And these horizontal orange lines are what are called the false alarm level. Basically, it's a bit of statistics, but basically you can ignore anything under that, and any peaks that go above the false alarm level might be real, but they still might not. They can often be caused by flukes in the data and sort of artifacts of the way the data was collected and the schedule the data was collected on. So we see in the periodogram for the integral observations, we see some very large peaks here on the left. Those are mostly likely to be due to the periodic nature of the observations themselves. Every few days, on a fairly regular schedule, there's a new set of observations, and that tends to show up in the periodogram. But what's more interesting is this smaller but wider set of peaks here around the 200 events per day mark. 200 variations a day is really, really rapid. It works out as it's every 7 minutes or every 17 minutes, something like that. That's really, really fast for any kind of periodic um, variability. But there is a type of periodic variable star that does change that rapidly. It's called a ROAP star or a rapidly oscillating AP star. Um, those stars, as you might guess from the name, tend to oscillate very, very quickly. But because of the physics of how that happens, those stars also cannot be rapidly rotating. And we know that HD 38451 is definitely rapidly rotating because you can see it in spectroscopy. And yet, if you look at the integral observations, it seems to have these very rapid variations as well. So those two things don't quite match up with each other, and that's potentially very interesting because if these 200 cycle per day variations were real, that would mean there's potentially a new physical process that's causing them. And who wouldn't want to be the one to discover an entirely new process in astrophysics? So what my supervisors and I decided to do was to try and get some better photometric data to try to verify whether or not these variations were real. And we did that using data from this satellite, the TESS satellite, the Transiting Exoplanet Survey satellite, which you may have heard of. This is still in operation now. It's searching for exoplanets and doing a fantastic job of finding exoplanets. TESS takes very, very high quality photometric measurements, and it does them very, very rapidly. What TESS is doing is searching for exoplanets using something called the transit method, where you look for the very small dips in brightness when a planet passes in front of its host star. And what TESS is doing is it spends about a month at a time looking at one single patch of the sky, and then it moves on to the next one. And for that month, it takes a new photometric measurement every few minutes. So that is perfect for us if we're trying to look at variations that are happening potentially every 10 or 20 minutes. That's those sorts of high cadence observations are exactly what we need to really try and see if those are real or if there's some sort of artifact in the data. And this is what the test light curve for HD 38451 looks like. I mean, that's a whole world apart from the integral light curve, which is mostly blank space. Here you see the TESS light curve has hundreds and hundreds of different measurements with just a few gaps that you can see. TESS, it observes continuously each sector for about a month, but it does have to they have to physically turn the satellite back towards Earth to downlink the data every couple of weeks. So you get a gap every 2 weeks where there's a downlink. And for HD 38451, we actually got lucky because of a fluke of where it's positioned on the sky. It wasn't just observed for 1 month, it was observed for several months consecutively. So we had a ton of data for this star from TESS. So I calculated a periodogram of the data, hoping to see whether or not we would see these integral these peaks that we see in the integral data. So this is what the TESS periodogram looks like. Much flatter than the integral one, and absolutely no sign of the 200 cycle a day variations. So that was a little disappointing. I was quite hopeful that we would discover something absolutely groundbreaking and new, but unfortunately that didn't happen this time. But it does still have these large peaks here on the left. Those don't appear to just be a fluke of the scheduling of the observations like they might have been with the integral data. So what you can do if you see a frequency on a periodogram like this, you can plot what's called a folded light curve to see if that variation may be real. And a folded light curve is basically where you plot the data on top of itself again and again at whatever the the period is. So say you think there might be a variation every 5 days, you would plot the first 5 days worth of data, and then you would go back to the start, plot the 6th day to the 10th day on top of that, and so on. If there is any kind of variability on that timescale, you'll see that come out in the graph very clearly. So I did attempt to do that originally with the integral data, with all of these periods that show up in the periodogram, and nothing really came out. But the data was so gappy, it was hard to tell if that was real or not. But when I did that with the largest frequencies here in the test periodogram, I got this. And it's a very shallow example, but it's almost a textbook example of a variability from stellar rotation. So I was quite excited when I saw this. This is my PhD thesis is quite long. There's hundreds of diagrams in the thesis. This is my favorite diagram for the entire thesis, just because it surprised me so much when I first drew it. So what you see is this nice sort of wave-like pattern as the brightness goes up and down on a very shallow sort of change. This is a tiny variation in brightness, absolutely tiny. You would never see this from ground-based observations. I'm pretty confident that I'm the first person to find this in the data for HD 38451. So yeah, I was quite excited when I found this. This kind of rotational variability comes about from inconsistencies in the brightness on the surface of the star. So there could be, in stars with strong magnetic fields, you can get permanent star spots or clusters of star spots that can rotate in and out of view and that sort of thing. And that can cause this kind of variation as that rotation happens. So with this particular frequency, this period, is equivalent to a rotation of 17 hours and 39 minutes and 37 seconds. That's pretty fast. It's also completely consistent with the 200 kilometers a second that Warner and Snedden found. So that's pretty exciting. I basically managed to confirm their result of the rotation using a different kind of measurement. A kind of measurement that just wouldn't have been possible when they wrote their paper. This also implies there may be some strong magnetic activity in the star, creating some long-lived star spots. So there are some astrophysical implications from this result as well. So that's exciting. I managed to confirm that this is a rapidly rotating star, but I didn't. We still the question of the change in color is still outstanding. So I attempted to take some color measurements of my own using this telescope here on the left. This is the Open University's Pirate Telescope, which is located in Tenerife. I did my PhD at the Open University, so I had access to their telescopes while I was doing that. So I scheduled many repeated observations using Pirate of HD 38451. Obviously, this is a relatively small, it's a 0.6 meter telescope. It's ground-based, so it doesn't have anywhere near the accuracy of something like TESS. But what it does have is several different color filters. So where TESS is just observing in broad white light, Pirate can give us a measure of different color measurements, how bright the star is in different parts of the spectrum. So what did I find comparing the color to what was found in the Warner and Snedden paper? I should say that when you do spectroscopy as a side effect, you also measure the color of the star, because of course you're taking a spectrum of the star. That's a different way of measuring the color from what I did. There's usually more than one way of measuring each thing. So Warner and Snedden, as well as their spectroscopic results, published some color measurements. I compared the present day color of the star to the color as it was in 1988. More or less, it's the same, except it is slightly less red than it was in the late 80s. So that could be a sign that there is still some ongoing change in the color here. If a mass loss event caused the original change in color, perhaps there's been some more recent mass loss events or some more recent more recent activity along those lines. Or perhaps it's a continuation of the change that Hind saw. Perhaps that massive change in colour from the mid 1800s is still ongoing today. Can't be sure at this point. More measurements would be required to get to the bottom of that. And that's something I intend to do in the coming years. It's whenever I have some spare time. I don't have any funding to study this star, but whenever I have some spare time, I intend to point a telescope at it and see what's going on and see if we can solve some of the outstanding mysteries. So just to recap, we know that HD 3451 is definitely a shell star. It's definitely rotating rapidly, and it probably has episodes of mass loss that would potentially explain the sudden change in colour. But there are still unresolved questions. If a mass loss event does explain the change in colour, why did the magnitude seem to change, seem to stay constant when the colour changed? Also, why are there these sporadic reports over the course of the last 100 years or so of irregular pulsations, and why don't we see any evidence of those now? So perhaps both those questions will be resolved by future observations. There are lots of all-sky surveys operating these days that basically take regular measurements of every star in the sky. Those have a good chance of seeing something if it happens. But the problem is, a lot of the all-sky surveys simply measure white light, and if what we're looking for is a change in color that doesn't change the brightness of the star, that might not show up in most of the all-sky surveys today. One slightly different all-sky survey is the Vera Rubin Observatory, which is just becoming operational now. That is doing an all-sky survey in multiple colors, but unfortunately, Rubin is so sensitive that it can't observe HD 38451 because it's too bright. It would saturate the camera. So what we need is long-term precise monitoring of the color of this star to get to the bottom of what's happening. Currently, we don't really have that, but that is it is something in the back of my mind, and it is something that I intend to come back to later in my career. So if I do manage to get to the bottom of this, I'll be sure to let you know. Thank you. And I should also say, so you can see on here, if you're on Blue Sky, I have a Blue Sky account and I have a website. I also have, as I think was mentioned at the start, I have a astronomy newsletter, which goes out once every fortnight, which you can subscribe to at 3alpha.space if you're interested in this sort of thing.
Adam, thank you very much for a very enjoyable talk, very informative as well. We're going to move on to questions and answers. Could I ask you to stop sharing your screen so I can see all the usual culprits? As usual, ladies and gentlemen, if you have a question, if you're online, a digital hand, please. If you are in the room, attract my attention. Roy will stick a microphone under your nose so people can hear your question. So I'm looking around for questions. Graham, in the room.
Historically, when did people first start defining the color of the star by any numerical feature? I mean, as degrees Kelvin, for instance. So how long ago was that first done?
Oh, that's a good question. Don't have a precise year in front of me, actually. I wouldn't like to guess.
Adam, can I butt in on there?
Yeah, go ahead.
The OBAFGKM classification on temperature, and I think that started with the Harvard University with Annie Jump Cannon, I believe, was the one that first defined that, and this dates back to about 1910.
There you go. Thank you, Roy.
Sorry, I've got a question myself, Paul.
Yep.
You don't want mine? This star that changed colour, you're talking about it having a very fast rotation, 200 kilometres per second. Presumably this will lead to a very large equatorial bulge on the star. as it's rotating at such a speed. And this will probably have some sort of great gravitational effect to the material that's thrown out. So it may be even ring-like, you know, a bit like Saturn brought it. You know, am I assuming correctly there?
Yes, actually. So shell stars are very similar and actually overlap a bit with another type of star called BE stars, which again are very rapidly rotating, and they do have so BE stars have a much more consistent mass loss effect around their equators. So what they actually have is, you've probably heard of an accretion disk where matter is falling onto a star or a black hole. BE stars have what's called a decretion disk where material is just flying off of their equators. So it's a very similar sort of star. Shell stars in general, I don't know if they tend to have disks and rings. I think it's more I think they're maybe on a slightly slower rotation than BE stars, I would guess. So it's more shell-like than ring-like. But yeah, there's sort of they overlap, so there's sort of a grey area between them, I think.
Okay. Peter Lloyd, online.
Yes, can I just take up a point that came out of that? You talked about the rotation speed of 200 kilometers per second. I thought you said that was a maximum possible speed, which I took to mean that it could be a great deal less.
That's right. If the star is inclined at quite a shallow angle, then it could be quite a bit less from the spectroscopy, that is. But with the photometric measurements from tests with the rotation that I found in there, that isn't subject to the inclination of the star. So we can tell from that it is definitely rotating at more or less the maximum speed. I think in my PhD thesis I did work out the inclination angle, but I can't remember the exact angle offhand.
Oh, yeah, I see. So you've got independent confirmation. It is at the upper end.
Yeah.
Okay, thank you very much.
Okay, I'm looking around for any other questions. I'm not seeing anything in the room. And oh, go on then, Lod.
How would that speed actually interact with sort of magneticity and sort of sunspots that you would see?
Well, I'm not an expert on the magnetic side of things, but the magnetic field in stars is caused by the rotation, I think. So the different layers inside the star sort of rotate at slightly different speeds. So the more rapid the rotation is, in total, then there's more energy there to sort of drive that magnetic sort of dynamo. So basically, that I believe, if I understand correctly, the faster the rotation, this just means there can be stronger magnetic fields sort of produced.
Okay, Lod. Did you catch that?
No, sorry, I couldn't hear that.
About magnetic fields having the effect on sunspots and different temperatures on the surface?
Yeah, so sunspots are caused by the magnetic field, sort of. So sunspots are cooler than the surrounding area because I'd have to. So I'm definitely not an expert on sunspots, but the magnetic field cools the surface at the point where the magnetic field lines sort of intersect with the material on the surface. So the stronger the magnetic field, I would guess the bigger and the darker the sunspots would be.
Okay, okay. Mike Scullin, online.
Hi, I was just finding my mute button. A lot of the measurements that you've mentioned through the talk depended on the frequency of the photons. And I don't even know if this is possible, does gravitational effects such as passing near a black hole, can photons get a gravitational assist and change the frequency? And would that affect your measurements, and has that been taken into account?
For a star, it won't have a measurable effect, but that for black holes, it definitely does. Yeah. That's so if you're observing, so for example, the famous image of the black hole at the center of M87 that was produced by the Event Horizon Telescope a few years ago, that was a radio observation. The light being emitted from close to the black hole would have actually been gamma rays. That's been redshifted so much that it's observed in radio. So yeah, you definitely see a gravitational redshift effect as well. But for this star, that won't have a measurable effect. But yeah, definitely for black holes, it is an important.
Yeah, I was meaning intervening black holes where the light.
Oh, I see.
Has been the photons have had a gravitational assist from a black hole that's in between your viewing and the object.
Oh, I see. I think any effect like that would be very small. So I don't think that's something that would affect the measurements.
It can happen then.
I'd have to guess. I think it probably could to some extent, but I don't think it would affect the light in general. Another similar effect is the microlensing effect that is actually part of my work, which is not really a change in frequency. It's the sort of a lensing effect where the light could be amplified by the gravity of a black hole. But that's a different effect, really.
Yeah. Okay. Thank you.
Henry, online.
Hello. I'm going back to the high rate of rotation. Does that how does that compare with the rate of rotation of our sun? And B, the very high rotation rate, does it suggest that it was once a very much larger star that has collapsed?
Last time I gave this talk, someone asked me what the rotation speed of the sun was. I didn't look it up and write it down. I should have done that. I think that if I remember correctly, the sun rotates once every few weeks. Can't remember what it is in kilometers per second, but it's a lot less than the 200.
It's about 26 days, isn't it?
26 days. So the fast rotation more than likely comes from has more than likely been there since the star formed, I think. So that the reason stars rotate at the speed they do is that the material that forms them will have some overall motion just by chance. When you compress the material down, that small motion also gets amplified. So the angular momentum is conserved. So when the volume of the cloud is compressed down to the size of a star, the speed of the star has to be, the rotation speed of the star has to be a lot higher than the rotation speed of the gas cloud that formed it, because it's so much smaller. So the rotation speed of the final rotation speed of the star will depend on all the properties of the cloud that formed it. So there'll be a lot of different factors that go into it. But I think the rotation almost certainly comes from how it was formed. I think there potentially could be other ways a star could kind of, the rotation speed could be affected by interactions with a binary companion and so on, but there isn't the star isn't in a binary system. It's just a single star.
Okay,
Thank
Henry.
you.
Okay, so I'm looking around for any final questions. I'm not seeing anything in the room, and I'm not seeing anything online. Ladies and gentlemen, that just leaves me to ask you to join me in giving Dr. Adam McMaster a big McMaster Astronomical Society. Thank you. Thank you very much, Adam.
Thank you. Thank you for having me.